area that is formed by revolving an arc, having looked at how to calculate arc length, and we also remember, we can recall how we used to find volume of surface formed by revolving some region. So imagine you have your curve here. As long as your function is above the x-axis, so that is to mean your f of x is greater than or equal to 0. So it's either in the first or second quadrant. So let's say this is f of x, y equal to f of x.
Excuse me, sir.
Yes, go ahead.
I can't see a screen.
Oh, is it because it's blurred or you completely cannot see anything?
I can see now.
Okay, let's try to do something like this. Okay, how is that?
Visible.
So just give me a moment. I need to put this thing in order. Okay, I think it's network problem. So otherwise I was explaining to say, imagine you have your function there, and let's say you want to have an arc length. So from A to say some point B. So meaning that this is your arc length from there up to there. And we have already discussed how we can calculate that. But today we want to imagine, or rather we want to understand what happens if we revolve, we rotate this about the x-axis, let's say. So you remember how to rotate this about the x-axis, just to see this same graph reflecting down below the x-axis. So to be something like that. So you can have something like that. I don't know if that's clear. Okay. So you can see clearly that you have this solid here that you are forming. Okay. So you are having that solid. So if you want to calculate the area now, you want to see how can you calculate this area that you are forming by rotating the arc that you had there. Okay. So if you look at this solid that we formed, my camera is really giving me a problem today. Are you able to see what is on the screen before we continue just talking to people what maybe you're not even seeing? Are you able to see what is on the screen?
Yes, though it's blared, but we can see.
Is it manageable?
We can see. Oh, I can see, but it is there.
Is it manageable?
Yes, it is.
Okay, so if it's manageable, then we can continue. So I was trying to explain, you see this surface that you are forming, you can calculate this area, right? So this is a solid that can occupy some volume. So you expect that there is space inside here. So you are talking of calculating the surface area. So look, this is just the outer part that you are seeing, but the surface area goes even behind what you are seeing. This is just a sketch. So this is the outer part, but you expect that this surface area is going around because this is a shape that is in solid form. So how do you calculate this surface area? So in your notes, you notice that it is denoted by sigma. Okay, so we just say sigma will be equal to, in this case, the integral from A to B, A to B. Now, because we are calculating this surface area all round, so we need to consider the whole angle, 360 degrees, which we call 2 pi in radians. Then we multiply by our function y, okay, multiplied by the arc length. So you know the formula for arc length is simply 1 plus y prime squared dx in this form. Okay. So that's the formula that we use. So we can also imagine, what if we are rotating this about the y-axis? Maybe there's no need of writing the sketch this time around. Of course, this can simplify to, you can remove the 2 pi outside, because this is just a constant. A to B, of course, your y there is just going to be f of x. I can rewrite this as, so y prime there, we know that is simply dy dx. Okay, so that would be the formula to find that surface area, which we call area formed by revolving an arc. So that would be the formula that we can use if you are rotating about the x-axis. Okay. So if you rotate about the y-axis, maybe let me just give you the formula without really writing what we are, the sketch. So we'll simply say that will now be 2 pi. So if you're rotating about the y-axis, the limits will no longer be for x, which are we call a and b. So we'll be talking of c to d. So that you'll be using the limits for y. Then here you have your x, okay? Then root of 1 plus x prime squared dy. Okay, so if you like, you could write this as, but what would be this, your x? So in this case, you are imagining that your function is not given as y equal to f of x. So your function is now given as x equals to f of y. So in this case, we can simplify this as 2 pi integral a to, I mean c to d what is our x? Is f of y. Then we'll have root of 1 plus. This our x prime is the same as the x dy, if you like. Then we square, we integrate with respect to y. Okay. So this is another notable formula that we can use when we are rotating about the y-axis. This is the formula. About the x-axis, this is going to be the formula. Okay. Now, we can also rotate about some line. It will not always be the x-axis or the y-axis. Okay, so let's imagine this case 1. If you want to call this case 1, let's call this case 2. Okay. We want to also see what happens, what formula do we use if we are rotating about some line. Okay, so if your curve is given as we had it in case 1, where y is equals to f of x, of course, this will only hold if your derivative function is continuous on the interval that you're using on that arc length. So this will be true when f prime of x is continuous. Okay, so this should be continuous on A to B, on that interval. Okay. That is to say, it is continuous on the arc that you are rotating. Okay, so I'll sort this problem of the camera when I'll be in a suitable venue. Because I see it's really giving us problems. But it will stabilize. Let's just continue. So, so if your function is given as we had it in our case 1, now what happens if you want to rotate about the line, say y equals to A? Okay. So let's say if we rotate about the line y equals to, let me say k. Okay, in this case, this implies that our area that we are talking about would be the integral, if we like, we bring out 2 pi integral from A to B. Okay, remember we had y. Okay, so that would be y minus k in this case, which is this line, this line which we are rotating about. Then you have your function, the formula for arc length here. It will be y prime squared dx. So we may call this case 3. Okay, also, if our function is given as x is equals to f of y, where f prime of y, or x prime, if you like, let me just say, where x prime is continuous on the interval C to D, and then you want to rotate the arc that starts from C to D, you want to rotate. Sometimes you could just say we are rotating the curve, by the way, but you're just concentrating on the arc. So if we rotate this curve, x equals to f of y, we rotate it about let's say the line x equals to, let's say n, and to try what would be the formula for the surface area. Just N1. Okay, this will be 2 pi integral from C to D. Of course, you have your x minus n. Then you have x prime squared dy. So we may call this case 4. So these are the formulas that we can use to find the resulting area from revolving an arc. So that is our case 4. Sorry. Okay, so this is our formula. We called case 3. Then here is our case 4. Okay. So let's look at an exam question that came on this. So let's start with this one that came from the test for 2020. Hope you are able to read that. You may want to write it down. I don't know. Are you able to see the last one here, this one, which came from test 1 for 2020? I'm not getting any feedback. Are you able to see what's on the screen?
Yes.
Okay, so the question is the arc of the function y equals to root x from the point 4,2 to, that should be 9. So 9,3 is rotated about the x-axis. Find the area of the resulting surface. Okay, so try to answer that one quickly. So the function we are using is y equals to root x, and we want to rotate this about the x-axis. So you may want to even sketch the function. So this will be the solution for this test 1, 2020 question. That was question 3, part B. So I've shared most of these papers. I know you already have them. So let's call this our solution. So we want to first understand where is that arc. So the function that we are using is y equals to root x. We already know the graph of that such a function is just going to be in that way. This is y equals to root x from first year. We can't, I don't think we have issues sketching that. So from the points are 4, 2. So that would be, let's say this is our 4. Of course, you see that when you plug in 4 there, you get 2. So that's all right. And 9, 3. So when I put 9 there, we should get 3 there. Okay, so that's our arc from there to there. So we rotate this about the x-axis, this one. So we expect, we have done the shell method of finding volume, we have done disk method. So we know how to rotate about the x-axis, you just go this way. So this is the rotated one. So if we rotate this, look, then the surface that we are talking about, if I should form this as a solid, it will be something like that. Now, what kind of a shape is this one? Something like a parabola, but it's a paraboloid. Eh? Okay.
So I was disconnected. I'm kind of with the previous page.
For the
Previous page.
okay, so I don't know if you mean the one we were writing down the formulas.
Yes, just that one.
Okay.
All right, thank you.
Okay. You're welcome. So since you are disconnected, we are answering this question. It came from test 1 for last year. So the question is the arc of the function y equals to root x from the point 4, 2 to the point 9, 3 is rotated about the x-axis. Find the area of the resulting surface. Okay. So we said we first just have to sketch the function, and then we can see clearly that this will be the surface we are talking about, this here. Okay, but it's going around. So this is the surface, the area we want to calculate. So if you want to write that as your sigma there, okay. So we'll just use, which case are we using here? Hello, which case are we going to use?
Case 1.
Okay, of course, we are going to use case 1. Our function is given as y is equals to f of x. So in this case, we just say sigma will be equal to 2 pi integral from, now from where to where? In order to give us the limits we are going to use. Hello. Anyway, from 4 to 9. And then we'll have y root of 1 plus y prime squared dx. Okay, but what is our y is simply root x. So we first need to understand what is y prime, where y prime in this case is going to be the derivative of square root of y, which is the same as x raised to the power half. Right, I meant square root of x, which is x to the power half. What would be the derivative? To just be 1 out of 2 root x, right? This implies that the square of this is going to be the square of this, which will be just, is it 1 over 4x? Because we know when we square this, it's just 1 out of 4x. Okay, now what would be 1 plus y prime squared is going to be 1 plus 1 out of 4x. Okay, I can make this a single fraction and say this is 4x plus 1 out of 4x. Okay. So that,
can you repeat on the y prime?
okay. So y prime, we are saying here our y is given as root x. But we know that root x is the same as x raised to the power half. Then we do the derivative of this, implies that y prime, we drop the power, we drop half. That's the rule of differentiation. We maintain x, we reduce the power by 1. What is 1 minus half is negative half. Okay, this is the power rule that we are using. But when you rewrite this nicely, it's just the same as 1 over 2 root x. Are you good there?
Yes, I am. Thank you.
Okay. So therefore, when we take the square root, therefore now our integral is now 2 pi from 4 to 9. What is our y? We said this is root x. And then we'll have the root of this, 4x plus 1 out of 4x dx. So what does this become? 2 pi integral 4 to 9. What do we do here? Anyone with an idea? How do we integrate? Is anyone getting me?
Yes.
But you guys, isn't this too easy to just answer? How do we integrate this? Okay, root x. So I know rules of indices that when I'm square rooting something like a fraction, I can take them separate, the square root of the numerator, square root of the denominator. So what I'll have is the root of 4x plus 1 divided by the root of 4x down there will just be 2 root x dx. Okay, clearly this and that cancels, and the 2 with the 2 outside cancels. So my integral is very easy. I'm simply having now pi outside and the integral of that. So therefore, this will just be pi integral 4 to 9 root of 4x plus 1 dx.
So I'm kindly asking for the previous page.
Okay, I'm afraid that the meeting is going to cut anytime soon, so I wanted us to finish it before it cuts.
Okay.
So we know now how to integrate this. This is a very easy integral. I can introduce, because the derivative of this guy is going to be 4. So I can introduce a 4 somewhere, or a special one, which is 4 out of 4, which I can write as pi over 4 integral 4 to 9 by 4 root of 4x plus 1 dx. Okay, so from here, I know that now I let u equal to 4x plus 1, du just going to be 4 dx, which I have here 4 dx. It's just going to be du. This implies that we have pi over 4 integral from u1 to u2 of 4 dx is just du. Then I'll have root u, which is u to the power half du. Very easy integral. This just becomes pi out of 4. So I add the 1 to half, that would be 3 over 2. I take the reciprocal, that would be 2 over 3. Then u raised to the power 3 over 2 from u1 to u2. What is that becoming? So 4, 2 into 4 is half. So half times 1 over 3 is going to be pi over 6. Then we replace what is our u. Our u is right there. 4x plus 1 raised to the power 3 over 2. Then now I can replace back my limits because I'm using x now. So I can take back 4 to 9. What will this give us? We plug in 9 here. That will be 9 by 4 is 36 plus 1, going to be 37. Then square root of 37 raised to the power 3, we know that will just be 37 root 37. Okay, then I plug in 4 here, that would be 4 by 4 is 16 plus 1, 17. Square root of 17 raised to the power 3, again will be 17 root of 17.